Good evening, ladies and gentlemen, and welcome to the SAIEE Building Services section, the second in our webinar Wednesday series on small wind energy, profitable small wind turbines. Before we start, a few webinar considerations. Attendees are reminded to ensure the volume is turned up on your device. Ensure you have a stable internet connection. This will ensure the streaming and audio will run smoothly. Attendees can ask questions via the questions panel located within the GoToWebinar control panel. By default, the control panel is located on the right-hand side of your screen. The chat function is reserved for webinar organizers and panelists to communicate with attendees. Attendees will not be able to chat with each other, however, are encouraged to ask questions. A recording of this webinar will be made available on the SAIEE YouTube channel under the Building Services playlist. You'll see the QR code on your screen that takes you to our YouTube channel. Please register, it's free. A certificate of attendance will be issued a few days after this webinar. I'd like to introduce you to our host for tonight, Mr. Mike Barker, who is a consulting electrical engineer and building services specialist with over 30 years of experience in energy systems for a sustainable built environment. He holds a BSc in electrical engineering from the University of KwaZulu-Natal. Barker has worked on many of Southern and East Africa's sustainable buildings, including the Durban International Convention Center, stadiums, and, for example, the Valpray Lead Gold Office in Heidelberg. In addition to his building services experience, he consults on sustainable buildings and smart campuses in cities. Over to you, Mike.
Great, thanks, Minx. Yeah, about that South African Institute's YouTube channel. The last I looked, there were probably about 370 webinars there or so from the last couple of years. And of course, Minx is running webinars every month, so there's always something new and something relevant. So well worth your time to pop across and have a look at that YouTube channel using the QR code or having a look at our website. Okay, so this is the second webinar on small wind turbines in a series of 3. Next month, I think it's the 2nd of April, we're running another webinar with colleagues from Eskom and the CSIR, and they'll be looking at a business case for a industrial park that would be using wind. Okay, last month we had Mike Berge from the USA, and he introduced small or distributed wind turbines based on his 40 years of experience. And we discussed how both in the UK, Europe, and the USA, and China as well, there's a growing interest in small units, and that there's strong support from government to look further than just the large wind farms that are so common and that we're used to. Mike explained how they redesigned their 2010 generation 10 kilowatt turbine, and how the new design, a 15 kilowatt unit, dropped the cost of energy by nearly 60%. Now, we just have to imagine if, let's say, China started churning out good quality wind turbines. We've seen what they've done with PV, with batteries, and more recently with electric vehicles and vehicles in general, cars in general. You can imagine where we'd be in a couple of years' time if they continued to improve both the quality and lowered the price. I think we'd be in for an interesting time. By the way, the other important point that Mike made is that small turbines can be produced locally in South Africa, in almost any South African city, from smaller factories. You're probably aware that any PV manufacturing plant is normally a massive automated factory, often with robotics, and not many jobs are created from that. But small wind units require skills and trades that already exist: millwrights, welders, machinists, electricians, and the like, and it can provide decent work for all. But tonight we're going to be turning back to take a look at South Africa, what is working locally, and just as important, what it's all costing and where the profitable business case is. Steve Fourie will discuss his experiences right here in South Africa. He's going to kick off. He's just installed many smaller units around the country. I will show how to deploy a small 15 kilowatt turbine in a profitable way on a farm in the Western Eastern Cape, a dairy farm. And then Henry Karosky is going to chip in, and he's going to grill us on our presentations and also take questions from the audience. Please use the question window that's available on the drop down on the right there, and post any questions as you think of them. Okay, so let's jump right in now, and let me introduce Steve. Steve's the kind of guy that when you meet him, you start wondering to yourself why you hadn't got hold of him maybe 10, 15 years ago. He's has a massive amount of knowledge about all things wind and renewables as well. He runs a web forum called the Power Forum, and he's got over 15 years of hands-on experience. He has additional expertise in biogas and hydroelectric. And Steve says he specializes in practical, sustainable living solutions, including rainwater harvesting. So it's the whole the sort of green building sustainability approach, water purification, and other technologies. And he's committed, of course, to educating consumers about energy efficiency. You probably need to go over and take a look at his website. We've also uploaded a couple of PDF files, including a price list on wind turbines, and you can go and download them. They should be available. I'm just having a look. We'll give you some feedback later on how to download those, but those should be available online right now that you can download. So this evening, Steve's going to focus on small-scale wind power and a range of products that he's got available. Steve, can we call you up, please?
Hello everyone. Nice to see you, and thanks for allowing me to take part in this presentation. Yes, Mike, I have a lot of information with regards to wind power, solar power, inverter systems, and all the technology surrounding it, and it's all based on experience. I can't call myself an engineer because I'm not a qualified engineer, but I do have a vast amount of experience, hands-on experience, and living experience with regards to renewable energy from the beginning to the end. I'm going to switch my camera off so I can start the presentation. So hopefully this works. There we go. Can everybody see my screen? I hope so.
Yes, indeed.
So, okay. So just in short, I represent the Power Forum store, P2Y Limited. We are a renewable energy online store that is supported by the powerforum.co.za. We work in partnership with that. Powerforum.co.za was created by my business partner. It's his brainchild. There we have over 34,000 members that access this free resource. To become a member is free. The information on the forum is free, and it is just a large resource of knowledge with regards to anything renewable. So now we can move on to the presentation. So basically, there's a couple of things I wanted to discuss with you. Obviously, first, the perception of wind power in the market at the moment. So, I wrote a whole lot of stuff on the screen. You can read through it if you want. I'm just going to just sort of talk about the problems we experience with wind power, specifically in South Africa. So there's a lot of product that has been brought in by people that does not have the experience and knowledge and the expertise to install these products and understand where they would be feasible or practical to utilize. So you'll find lots of little rooftop installations with these little twirly-whirly turbines on top and these tiny little things attached to walls and all over the country. And then you hear people complaining about how terrible these products are because they're not producing energy. you know, and if the consumer doesn't understand how the technology works, and the installer that's supposed to facilitate the product doesn't understand how the technology works, how do you expect a product to perform the way it should, you know? So there's lots of factors that you've got to consider, you know, the environmental factor. You've got to make sure there's feasible wind speeds. The location is a very important factor in the installation of a turbine. There's lots of misconceptions about wind turbines. You know, firstly, a lot of people complain about the aesthetics. A lot of people complain about the noise factors, and then you know, all of those things come back to a very specific thing. It's utilizing the correct solution for the problem that you've got. So if you require wind energy and you are in an area that wind energy is viable, then choosing the right product is very important. And that's where we are lacking currently in South Africa, is people in the industry that have knowledge and understanding of what is going to sort of work, what's going to be viable. You know, South Africa does not have very high average wind speeds. And a lot of the problems with these wind turbines that are being brought in from China and all over the world is that these turbines are designed to function in very high average wind speeds. We're talking 12 meters a second. 12 meters a second is over 40 kilometers. I think it's about 43.2 kilometers per hour, plus minus. You know, and we don't have a constant wind of 43 kilometers per hour blowing anywhere in South Africa, 24 hours a day, 7 days a week, 365 days a year. Our average wind speed is more between 6 and 8 meters per second. And we do have some nice areas where the average wind speeds are above that, but then we're starting to look at, you know, either very coastal areas, especially the West Coast, or the Eastern Cape on high elevations where we have such high averages. But in general, your average wind speed is anything between 6 and 8 meters per second. Now, the problem with these high-speed wind turbines is that they require, because they require such a high wind speed to generate the energy, means that at a low wind speed, they produce very little, if any, usable energy. So I'm going to go to the next slide. I mean, I've covered a lot of the perception about the products. We can go to the next slide, and you know, the technical problems that we experience. And there I mentioned we sell a product called the HYE wind turbine. It's a 1 kilowatt turbine, and it's rated at 12 meters per second, which is 43.2 kilometers per hour. And if the wind blows at that speed in a perfect scenario with no turbulence, then that turbine is going to produce 1 kilowatt per hour. Now, and that turbine is a fixed blade turbine, right? So if the wind blows at 80 kilometers per hour, which happens a lot in South Africa because we get a lot of storms, then that little turbine now has a problem. Because it's got fixed blades, it's going to have the risk of throwing a blade because the rotational speed of the rotor is going to be high. You have the risk of it overheating the stator or the windings in the generator. You're going to have all sorts of problems that can occur that's going to cause that turbine to damage. We have had a lot of these 1 kilowatt turbines installed specifically at internet high sites or wireless high-speed high sites. And the problem we found with these turbines is that, especially, and there the wind can get to 80, 90 kilometers per hour quite easily. We've had that these turbines throw blades and or the bearings on the generator seize and things like that. Now, in a scenario where they're in a high site like that, they're not suitable because of the fact that there they can achieve very, very high wind speed. Now you take that same turbine and you install it in a residential application or on a farm to produce energy for whatever you need energy produced for, be it running a borehole pump or you know, powering irrigation pump or powering internet equipment. And in the area where you've got this equipment located, your average wind speed is only going to be 6 meters per second. Now at 6 meters per second, that 1 kilowatt turbine is only going to produce 200 watts per hour. which doesn't make it feasible. So you've got this big expense of putting this machine up. You've got the tower, you've got concrete, you've got all of the other sort of bits and bobs required to make it work. And you've invested, argument's sake, 60 or 70,000 rand, and the machine's producing 200 watts an hour. That means it's going to take 15 years before it actually generates enough energy to pay for itself. So choosing the right product for the right solution is very important. The problem with the fixed blade turbines we found is because of the fact that they're so limited in what they can do to prevent overrun. In other words, running faster than what they're designed to produce their power at. They use methods like resistive braking. In other words, there's a dump load coupled to its controller, and any excess energy is then sent to the dump load, and that will reduce the rotational speed of the turbine. But the dump load is only effective up to about 50, 60 kilometers an hour wind. After that, the turbine then either has to flip its tail out of the wind, or the tail is designed to cause the head to turn out of the wind and to prevent the machine from running faster than it should. So in our conditions, fixed blade turbines are not feasible in reality because of those problems. There's so many things that can go wrong with those things. And that in itself has created a very bad impression in South Africa with regards to wind turbines, because again, people don't consider all of these factors. That these machines, they have to come up with all sorts of interesting methods to avoid overrun. Now, there's other products we do, like the Bornay wind turbine. Bornay claims the turbines are the best in the world. If you speak to Mr. Bornay himself in Spain, he will tell you that exactly. However, his turbines also fixed blade, but he uses a different methodology to reduce rotational speed. It's a form of yawing, and the turbine's head lifts out of the wind as the wind speed increases. So it's got sort of like a resistive load that allows the turbine's head to lift, and then that reduces the rotational speed or the surface area of the blades into the wind. It does work well, but these turbines also require 12 meters per second to generate their power, which makes them unusable in South African conditions, and they all use high RPM generators. Now, that's where the big problem lies. Is a high RPM generator can be very small, it's very lightweight, it has very little copper, very little magnets, metal inside it. It's a very lightweight little thing. As an example, that HYE 1 kilowatt turbine weighs 28 kilograms, but it requires 750 revolutions per minute to generate 1 kilowatt per hour. Now, if you look at a low RPM wind turbine generator, then the low RPM wind turbine generator in equivalent capacity only requires 360 RPM to produce 1 kilowatt per hour. But for that turbine, you have to have very large blades. Now, if you utilize fixed blades and you put very large blades onto a fixed blade wind turbine, then you've got that problem when you do have that stormy day, we've got 60 or 80 k's an hour wind, then you're going to end up with the turbine throwing blades and the rotational speeds becoming ridiculously high, etc., etc. So we're back at the same problem. So that is the sort of like the short and the long of why we prefer, not to utilize high RPM, high wind speed turbines in South Africa. And there's very, very few products in the market that actually offer a low RPM solution. I mean, we've spent thousands and thousands of rands in research and development in actually finding a solution that will work in South Africa. Now, a lot of people have this very romantic idea about the vertical axis turbines, and apologies to anybody that really do support that product, but science is very much against vertical axis turbines in the sense that these devices firstly have no method other than resistive braking or mechanical braking systems to reduce rotational speed on the rotors. So if they do experience very high winds, we found that these turbines typically, the gyroscopical forces become so high, and the moment there's a very sort of like strong wind direction change, then it causes a torsional effect on the central shaft of this vertical axis turbine, causes it to bend, and then the turbine starts wobbling and it falls apart. Now, I have still to see someone develop a variable pitch vertical axis turbine. I think it would be quite a successful product because it'll overcome a lot of the problems that people, that vertical axis turbines do experience, and it may make them a slightly more feasible solution. However, the products that are available in South Africa all are rated at 12 meters per second. Again, they still use high RPM generators instead of low RPM generators. So the current product availability in vertical axis turbines, we tend to avoid those products as much as possible because of the potential failure of the physical device. And we've lost quite a bit of money thanks to vertical axis turbines. And we brought very good quality, in our opinion, very good quality products in. But the reality is that they were very unreliable. They were very costly to keep going. And I think that also, a lot of these vertical axis turbines that people bring into the market cause this conception that wind power is not feasible because they're not reliable and they've got all sorts of issues and troubles. But again, it very much so comes down to your product choice. You have to choose the right product for the solution. And also the people that sell these things to the consumers need to be honest about what the products really can do. And I think it's either that maybe they're not dishonest, just maybe they don't understand it, or maybe they're ignorant about what the true situation about wind power is. But anyway, so let's move on from the technical problems. I mean, there's a lot of stuff that I've written on this presentation. It basically comes down to that fixed blade turbines. The problem with them is that potential of having excessive rotational speed on the rotors, which causes excessive voltage, excessive current, can cause massive damage to the machine. Typically, when these things fail, they fail permanently. In other words, beyond repair, you've got to buy a new one when they break. And that's basically the short and long of the technical issues I find with the fixed blade turbines. Now, the next one is the generators that I mentioned earlier, the high RPM generators versus the low RPM generators. I've got a lot of engineers that will listen to this, and I'm sure they'll confirm what I say. The high RPM generators cost very little to manufacture. The low RPM generators cost a lot more to manufacture. Obviously, more copper, more magnets, more material required to manufacture them. The high RPM range generators have got a very narrow power band, which means that the closer it gets to its nominal rating, let's say argument's sake, the nominal rating is 1 kilowatt, and it requires a wind speed of 12 meters a second, then if the wind's blowing at 8 meters a second, the difference is going to be more than 50% of the production on a high RPM generator. But if you go to a low RPM generator, then the lower the revolutions become for the same generation capacity, the wider the power band becomes, which means that even if the 1 kilowatt low RPM generator is rotating at, argument's sake, 150 RPM, it's going to be producing close to 50% of its capacity, even though the maximum rating on the generator is 360 RPM. So on the next slide, I have an example between two products that we sell. I use the products not because we sell them, I use the products because they both give you sort of like a really ideal illustration of the difference between a low RPM generator versus a high RPM generator. Now, if you look at on the left side, you'll see there's the power curve for the HYE 1 kilowatt. Now, the reason why we sell the HYE, just out of interest sake, is it's a very popular product in America to use. And what the guys in America do, because they don't have such strict municipal regulations and problems like we have in South Africa, they can stick that turbine at 36 meters, into a jet stream where it experiences a constant wind of, argument's sake, 10 meters per second, 24 hours a day. And, then that little turbine is generating 1 kilowatt per hour. In South Africa, we don't have that privilege. So we are limited to, I think, as far as I know, that the municipal regulation or the general regulation around South Africa is 15 meters is the maximum tower height. If your wind turbine tower is higher than that, then you've got to get what they call an environmental assessment study done to facilitate that. But let's get back to the power curve. So on the left, you've got the HYE turbine, which is a high RPM turbine that generates 1 kilowatt at 750 RPM. But now we're looking at wind speed here. So at a wind speed of 12 meters per second, that little turbine is going to produce 1 kilowatt per hour. Now, if we look at our low RPM, and that is now one of our products, the Odin variable pitch wind turbine, that turbine generates 1 kilowatt at 360 RPM. But in a wind speed of 8 meters per second, it generates 1 kilowatt per hour versus the HYE that needs 12 meters per second to generate generate 1 kilowatt per hour. Now, if we go down to the sort of like the low end average for South Africa, which is a 6 meters per second wind, 21.6 kilometers per hour, and we compare apples to apples now, and we'll see that the power curve on the HYE at 6 meters per second shows that it produces 200 watts in a 6 meters per second wind, where the Odin turbine at 6 meters per second is producing 450 watts. So that's over 50% more energy at the same wind speed. So you can see what a big difference a low RPM generator makes versus a high RPM generator. And that is what we sort of are moving towards, is looking at low RPM generator wind turbines with large blade areas. But now the large blade area, if it's in a fixed blade formation, you've got problems. Because what are you going to do when the wind blows really strong and you've got a massive surface area in the wind? And that's where the variable pitch technology comes in. You can control the surface area of your blade as the wind speed increases. So if you look at the power curve on the HYE turbine versus the power curve on the Odin turbine, you will see that the HYE turbine at 18 meters a second is sort of like its theoretical maximum, and then you've got to stop the machine because you risk damaging components in the machine. But the Odin turbine can sustain its roughly around 1.2 to 1.3 kilowatt production all the way to 24. Actually, we didn't bother taking the curve further, but it'll actually carry on right up to 25 meters a second. And then as the curve rose evenly, the curve will drop off evenly. So that means that the variable pitch turbine can run indefinitely without having to be stopped. Doesn't matter what the wind speed is. You don't have to run outside and put brakes onto it to protect the machine because it's going to self-destruct. The fact is, it retains, it's just like having a governor on a diesel engine or a petrol engine, a rev limiter. That is what the variable pitch mechanism does for the variable pitch machines. It limits the revs to prevent it from damaging itself. And there's so many benefits to that advantage. And obviously now, that allows us then to utilize much bigger blade diameter, much larger blades, much larger surface area that increases the energy, sort of the kinetic energy transfer, from the wind to the generator a lot, and that allows us to generate more power at lower wind speeds. So that is why these type of turbines do have a very good potential in South Africa specifically. Now I'll move to the next slide. Now there's additional technical information about I've mentioned here the fact that all the small wind turbines, the blades drive the generator directly. There's no gearboxes, there's no transfer cases, there's no drive belts. So that obviously makes the production of this product a lot cheaper to produce, and that does make it feasible, like Mike mentioned, to produce wind turbines in South Africa. We have looked at doing that in South Africa, but currently we're still having our turbines manufactured in China. It just works out 5 times cheaper than having it manufactured in South Africa. But hopefully in the future we will achieve a point where it would be financially feasible to produce these things locally. But yes, now the small wind turbines, there's many advantages to them. The fact that they don't have gearboxes, the cost of manufacture, the simplicity of the design, the mounting structures required to mount them is a lot cheaper, reduced maintenance costs. I mean, if you look at a wind turbine, you've got bearings in the generator, a front and a rear bearing. You've got a bearing in the neck, which allows the turbine to change direction. And typically there's 2 in the bottom and the top bearing. The bottom one would be bigger and the top one would be a little bit smaller. And then you've got a brush kit and a couple of slip rings that transfers the energy from the generator to your cable that will go to your controller. But the point is, the simplicity of the design of the wind turbine, the small scale turbines, is what makes them quite attractive. Now, we've got a big machine like our 10 kilowatt machine. It's quite an expensive machine, but for a full maintenance and service kit for our 10 kilowatt machine, you're looking at about 4,500 rand. And typically, you just overhaul the machine every 15 years, depending on the wind conditions. But there's a lot of important factors about turbines that people must realize. Is a turbine, because it's got moving components and moving parts, it does require a little bit of attention. And I'm not saying every week you've got to maintain the machine. Typically, it's if the turbine's installed in a very high wind area where there's 12 to 15 meters a second wind permanently, and the wind is very sort of like, it changes a lot of direction and gusty, then I'd recommend lower the machine down once every 6 months, make sure that all the bolts, nuts and stuff is tightened up, check the grease nipples, make sure they're greased properly, just do a visual inspection, basic maintenance. If there's any excessive play on any one of the components or movement, then okay, it's time to replace a bearing or it's time to replace a component. And the cost of those components, because it's such a simple machine, is relatively inexpensive. And over the lifespan of the machine, theoretically speaking, you can keep a small scale wind turbine working for 100 years. And the reason I say so is, as long as the generator or actually just the magnets, on the rotor, as long as they're not exposed to physical damage, like someone hitting it with a hammer, or overheating, then those neodymium magnets will only lose roughly about 2% of their capacity every 100 years. So as long as you maintain the machine and look after the components inside, you're going to end up with a machine that's going to last generations or lifetimes, if that makes sense. It's simple maintenance. But I see my time's almost, my time is getting tight here, so I'll quickly move on. So I have sort of like already touched a little bit on the advanced variable pitch technology. Now, there's lots of different variable pitch technologies available in a small scale wind turbines. I'll quickly run through it. What we're focusing on on the products in South Africa, there is another brand of wind turbine in South Africa that also does variable pitch wind turbines. I'll mention them, and they do deserve a mention. It's Kestrel. Their 3 kilowatt turbine now also have a variable pitch technology. I don't know exactly how their system works. I haven't really investigated it, but our system is also a mechanical variable pitch mechanism. It uses a spring and a couple of counterweights that is rated correctly, and it'll automatically just pitch the blades as the wind speed increases. The benefits you have from that is constant RPM, constant energy production, obviously far less wear and tear because your machine never runs faster than it needs to run. You don't risk blowing up your controller because you're never sending too much voltage or too much current to the controller. There's just so many advantages to having a variable pitch turbine versus the fixed blade turbine. And also obviously the fact that you can leave it running in a wind speed of 90 kilometers per hour without worrying that the machine's going to self-destruct, which is quite an advantage. And that also then adds into your average production throughout the year, because the less the machine stands still, the more energy it's producing. So you want to have that machine running as much as possible. And yeah, I mean, that's very, very simple. So other benefits is also obviously because it doesn't overrun, it can't throw blades, which makes it a lot safer around humans and around residential areas. And then obviously the one big benefit of the variable pitch is obviously noise. Once the turbine reaches its sort of nominal wind speed, it will sort of, like the 1 kilowatt, it makes about 60 decibels in a wind speed of 8 meters a second, which is its nominal wind speed, at something like 25 meters. When the wind speed increases above its nominal speed, the turbine doesn't spin faster and faster, which means the noise of the turbine doesn't become more. Your fixed blade turbine, when it's sitting in a wind speed of 60 kilometers an hour, I've got personal experience, sounds like a chopper taking. It's very loud. Where your variable pitch machine, you don't have that problem. So that sort of makes it a lot nicer and easier to install in a residential application if required. But the problem is still, it is a horizontal axis machine. It does need to be high off the ground, it does have to be higher than anything around it for you know, depending on the height of the tower, but there's a formula that you can use. I typically say to the client, you know, at least 450 meters diameter around where you're putting your little 2 or 3 kilowatt machine, and you know, the ground turbulence wouldn't be so bad, and the machine would definitely still be producing energy. But you know, objects on the ground, trees and buildings and structures do have an effect on how efficient the machines work, because you know, the data sheets or the power curves are based on ideal wind conditions, you know, no turbulence. So the moment you put it into real world situation, I've got turbulence, you've got the wind direction changes, all sorts of things like that that affect how efficiently the machine produces power. You also have, you know, height above sea level, density of the air, all those kind of things have factors will play a role in how efficiently that turbine is going to generate energy. You know, hopefully that all makes a bit of sense. But yeah, so the variable pitch mechanisms, the big benefit that it gives us is it allows us to put much larger blades or much larger surface area blades onto our turbines. That's why 1 kilowatt turbine's got a 4 meter blade diameter. You know, that allows a lot of blade area, and that's why the machine can generate so much power at such a low wind speed. You know, the HYE machine has only got a 1.5 meter blade diameter. It's a tiny little machine in comparison. It weighs 28 kilograms. The low RPM generator weighs 110 kilograms, just to give you a bit of context. So yeah, so I've covered it, the variable pitch technology. You're welcome to read through it further later. Then obviously the small wind turbine integration method. So I wrote a lot of stuff here. I'll try and condense it quickly into 5 minutes. So small wind turbine integration technology, your first method of integration, and that used to be the historical method, was to couple the wind turbines to a battery. And in the old days, we didn't have access to lead acid batteries. We didn't have access to lithium. We only had access to lead acid batteries. So now we've got lithium batteries. Wonderful evolution to solar energy. It's made solar energy definitely you know, a reliable, viable solution for permanent energy generation. But so now, how do we integrate the wind turbine? So we can integrate the wind turbine to the lithium battery, and the controllers we use are very advanced. They've got Modbus protocols, RS-485 comms. We can even tell the wind turbines to start and stop remotely through those protocols. We can make the wind turbine produce either 48 volt, 51.2 volts, or 600 volt DC. It just depends on the lithium solution that it's attached to. However, it is voltage based, unfortunately. So which means that if the battery is fully charged, the wind turbine is not going to work. It's simply not going to run because the energy's got nowhere to go. So the turbine will stand still. The moment the battery starts discharging, then the turbine will start working and it will generate energy. And as long as the energy being generated by the turbine, or let's put it this way, as long as the energy being consumed by the turbine is equal or less to what the turbine is generating, the battery is going to not discharge, and it'll charge the battery simultaneously. But if the load exceeds the generation power of the turbine, then it'll utilize the energy from the turbine automatically from the battery, as if it's discharging battery energy, but it's not. It's using wind turbine energy. So that's the one method of integration. A lot of explanations on voltages and et cetera, et cetera. The next integration would be if we couple it to MPPT. Now, we'll use the similar controller. It's slightly different. It's a little bit more advanced. And there we can make the controller output either 360 volt DC or 600 volt DC onto a SunSync or a dia inverter, where we couple the turbines then directly to the MPPTs of that inverter, and we program the MPPT. We program a power curve for the turbine into the MPPT, and then the dia inverter or the SunSync inverter will just utilize the energy as of its solar power. Very, very efficient method. Your turbine is probably going to be generating the most energy in that configuration, because it means that it's not going to compete with MPPTs to charge a battery. It's going to be producing energy with the MPPTs for loads. And when the MPPTs and when the solar power stops producing energy, the wind turbine is still going to be producing energy via the MPPT, and so that power can then be used directly for loads, etc., etc. Obviously, the benefit of having the constant voltage from the variable pitch turbine is quite a benefit, because then the power delivery is going to be nice and smooth, etc., etc. So that covers the MPPT coupling method. The next method is going to be AC coupling. Now, AC coupling, there's a couple of options in AC coupling. So AC coupling, we utilize a grid-tied wind turbine inverter, and the wind turbine couples directly to the grid-tied wind turbine inverter, and the grid-tied wind turbine inverter outputs 230-volt AC at 50 hertz in single phase, or 380-volt AC at 50 hertz in three-phase. The single-phase models that do not come with CT clamps, but it doesn't matter, because when you coupling into a Solis or a SunSync or a Dia inverter to the generator aux port, the settings on the port regulates how much energy the wind turbine will be pushing in, but it will be pushing it in at 230-volt AC, because the SunSync or Dia or Solis inverter is going to act like the grid for the grid-tied inverter. Now, typically, the normal application for that would have been you just couple it to the ESCOM side of your system, and it'll generate energy into the grid for loads, and any excess energy will be exported. The three-phase models do come with the CT clamps, which allows export limitations, so you don't push energy back into the grid, but they all have anti-islanding and all of those functionalities built in. Obviously, they have to be within the world standards, which they are. So they're not going to kill an electrician that's working on ESCOM. If ESCOM goes off and they're connected to the grid side, they'll switch off, just like any grid-tied inverter should. But yes, so on your integration with the GenPort, I like this method a lot, because it frees up the MPPTs on the inverters, and I can still put in a wind power source into the system. And obviously, with AC coupling, if you go on PCS solutions, we can go as large as 100 kilowatt wind turbines with 100 kilowatt grid-tied inverters that are coupled to their systems in off-grid mode, which makes for a much better sort of off-grid solution, where you have a large-scale setup like a farm, or you've got a factory that needs to be run. Then you can integrate much larger small-scale turbines into the system. And obviously, like I said, we don't sacrifice MPPTs. And yeah, I mean, I think that covers most of the integrations and how we utilize wind power. Obviously, there's lots of advantages and reasons to buy, to go with wind power. If you look at a small 2 kilowatt wind turbine, that's going to produce in an average wind speed of 6 meters a second, which is like 21.6 kilometers per hour. It's going to produce 16.4 kilowatts of energy per day. Now, 16.4 kilowatts of energy is 16.4 units of energy. That's roughly 683 watts per hour. Now, what benefit is your system going to get? Well, firstly, you're reducing your base load at 683 watts per hour. You're reducing roughly 10 to 12 kilowatt hours of battery usage, because if the sun's not shining, you're running off battery. So if you add a wind turbine and it's producing energy, then you're not running off battery, you're using the energy produced by the wind turbine. So that, theoretically speaking, can reduce the load on the battery, or the consumption from the battery, or the cycling of the battery, between 10 and 12 kilowatt hours. If you're building a new system, that means you can exclude 10 to 12 kilowatt hours of battery storage, which would reduce the cost of that system considerably. So there's lots of ways to look at it. Turbines, obviously, is not a theft item. People don't like to steal it. They don't understand it, so they're not going to steal it. It's not easy to carry away. It doesn't take up a lot of space. It's got a very small footprint. Much smaller than what solar power has. And obviously, the higher the average wind speed goes, the bigger the solar comparison would be on the footprint. You can install wind turbines on farms. Animals can graze under it. You can still grow crops under the turbines. On the small scale turbines, 99% of the turbines recyclable. It's not like those big turbines that have tons and tons of fiberglass and concrete. Small turbines don't kill birds and bats because they move too fast. A bird's not going to fly through an object that looks like a solid wall. People are under a misconception when it comes to that, because if you look at the large turbines in South Africa, like the 7 megawatts and the 12 megawatt turbines, you're looking at a blade diameter or blade length of 210 meters. They have to regulate the rotational speed of those machines on the tips of the turbine blades to be below 750 kilometers per hour, or below the speed of sound. So yeah, I mean, if a bird of prey flies towards that, it thinks that blade's turning slowly, but in the meantime it's moving at 750 kilometers per hour. It's going to kill the bird. But the smaller turbines, the blades move too fast and they appear solid. So no, they don't kill birds. The variable pitch machines don't cause noise pollution. The fixed blades do, unfortunately. And I think the variable pitch machines are very pretty because they don't have tails. You know, they don't have tail vanes. They sort of like look like those big machines. They can generate power 24 hours a day. So, you know, and when it comes to ROI calculations, which I'll show you just now, they are definitely financially viable. Anything from 6 meters a second upwards, they become more and more viable. So, and in comparison with solar power, it's very competitive. They've got a very long service life. They can outlive solar by many, many years, or lifetimes for that matter. And that includes the inverters, the batteries, and the solar panels. And then very inexpensive to maintain and keep going. You know, so solar panels cost me more to maintain than my wind turbine does. A wind turbine I maintain once a year. My solar panels I have to have washed and cleaned once every, 2 months or 3 months. Otherwise, I start producing less. And that costs me $500 a day for 2 people to come and walk on my roof all day long to clean the solar panels without damaging them. So yeah, I mean, you've got to consider a lot of things here. Yeah, so I think I've covered that. ROI calculations. I mean, I think we've reached a point where we can sort of go to Q&A. This is just a bit about my business, what we do. I've got a couple of ROI calculations here that I can show you. So on the smallest machine, the ROI calculation is going to look the worst. So you'll see at a wind speed of 6 meters per second, this is now figures based on 2024. I haven't updated this properly yet. I just haven't had the time to really update it properly. But at 6 meters a second, your ROI is just under 4 years on a what machine am I looking at here? The 1 kilowatt turbine. But the cost of turbine is incorrect. Cost of turbine is completely incorrect. The cost of turbine is probably going to be around about 70,000 rand. So I think the one kilowatt is the wrong one to look at. Let's look at one that I know is right. The 2 kilowatt. 2 kilowatts right. Okay, here we go. So 2 kilowatt turbine, which is now obviously double the capacity and slightly more expensive than the 1 kilowatt. You look, at 21.6 kilometers per hour, 6 meters a second. You're looking at an ROI of 4 years. That's your cost, roughly, including the materials and the tower and the controller. Obviously, it doesn't include your solar system. Your solar system is separate, but that's the cost of the hardware. And in a wind speed of 6 meters a second, the machine is going to generate 16.4 kilowatts roughly a day, and it will take 4 years to pay for itself. If the wind speed increases from 6 to 7 meters a second, your ROI jumps up with 1 year. If your wind speed is 8 meters a second, and there's lots of farms around South Africa that have 8 meters a second to 9 meters a second, then your ROI is almost 2.5 years. So you can see that and I'm basing it on the electricity price of roughly 345 kilowatt hour. I mean, that's sort of like the residential going rate, or was the residential going rate in South Africa. I think it's going to be a lot more this year once the increases kick in, because the municipalities will also bump and boost their sort of costs. Okay, all right. So I think I've covered everything. Let's hand over to Mike.
Yeah, thanks, Steve. We'll have plenty of questions for you come question time. And let's just get my presentation up. Thanks, Minx. Okay, you should be able to see something there, guys. So
we have your screen.
Thank you. We're going to take a look at a case study, and the idea is to understand how to deploy profitable wind turbines. And in this case, we're going to look at a a modern farm, an all-electric farm, and try and understand how we can integrate these wind turbines into a local energy system, or as we can call it, a microgrid. So there's a lot of ways to design a microgrid using photovoltaics, batteries, wind, and of course connected to the grid, and in the background the odd diesel genset. Probably the right way to do it would be to use one of the optimization packages available now. There are plenty of them on the market. The ones we tend to choose, I think, would be those that are recognized by the World Bank, because if you run these calculations, you can take it to any bank and they'll accept the outputs, and certainly they'd be looking at what you're offering as a bankable solution. In other words, there's going to be money available. So the way let's take the DERCAM system, American system, probably about 25 years old. The way it works is you have a number of inputs, the tariffs, Eskom tariffs, for example, your consumption load profiles, we'll discuss a bit about that. Clearly, weather and climate data play a big part, solar and wind, and then the different technologies, PV, batteries, energy storage, and of course wind turbines. And then the way you configure it, you push all of that into the system as your inputs, you choose your objective. Typically you're going to look at energy costs. In South Africa, of course, redundancy, energy security is an issue. Carbon tends to be a bit of an afterthought, and so we'll leave that. At the end of the day, what you do get is a set of performance metrics, which the banks like to see, and then of course the all-important investment decision. How much wind, how much PV, how much battery, what should you be looking at, and what would be the optimum approach given the consumption load profiles and the tariffs. And of course, you'd want to do this over a period of, let's say, 20 years, so that you can understand where you're going. So when you look at the timeline analysis, the data that you push into these models, typically you would want to better understand the cost of diesel, for example, for your emergency generation, certainly the Eskom tariffs. And whilst a lot of things start to rise in terms of their cost, we all know that the batteries and the PV costs are going down. So all of this is factored in over, let's say, 20 years. And that's exactly why the banks like this sort of analysis, because they need to know whether this is going to work and their money, whether it's a good investment, that their money is safe. Now, we genuinely don't know what the future looks like, most of us. So we run many scenarios. We can run scenarios where the cost of Eskom power goes down after 10 years. There's a thought. We can run scenarios where carbon tax is introduced with a vengeance in say 10 years time. So we can add all of this together, and by running many scenarios, we can get a better understanding of where we're going. One of the things that just about everybody understands, and as a member of the IEEE and the South African Institute of Electrical Engineers, we're starting to understand that locally generated energy is less expensive, and the reasons are quite simple. If you look at this graph, this is a graph produced nearly 15 years ago by Ernst & Young, and what they're showing is that whilst the cost of energy might not change much, the cost of moving those electrons, whether they're gray electrons or green electrons, from wherever to your doorstep will continue to rise. The cost of transmission and distribution is going up all the time. And of course, going the other way is the cost of solar and batteries. So we're pretty close to tipping point number one. I think there's no argument about that. Tipping point number two is about electric vehicles and petrol diesel engines being on price parity there. Some would argue that we're almost there. And of course, the tipping point number three, I think, is where a lot of big changes are going to happen. And this is our future. We're going to reach a point where the cost of moving electrons from wherever to your doorstep is going to be a lot more than the cost of generating locally. So we're going to see a lot of local generation, and this is, I think it's a given, but not everybody accepts that just yet, because, you know, the future is never clear. So if we look at the 25-26 Eskom tariff that has recently been introduced a couple of days ago, we see that were you to be a farmer, the couple of tariffs apply to you. The RURAFlex tariff for the rural 11 kV spells out exactly how much you're going to be paying. Interestingly enough, during the high season, a kilowatt hours is around about 7 Rand. That's quite a big jump from where we are at the moment. And another interesting, if you can see my cursor, is the legacy charge. So for every kilowatt you use, you're paying roughly about 23 cents to satisfy the cost needs of all the legacy solar farms and wind farms that you see around the country at the moment. And this is not unusual. The guys in the UK are paying a larger amount. And to a degree, you know, people get a little bit bitter about this, but that's the cost of progress, I guess. So anyway, we take all these numbers from the tariff. This is the Eskom tariff, and we start pushing it into our system. Important, of course, is to understand that time of use, certainly for a larger farm, time of use becomes pretty important. So if we're probably familiar with this. What they have done is they've changed from 3 hours peak to 2 hours in the morning, and they've introduced 3 hours at night. So there's been a change there. But by and large, the time of use tariffs are much the same as they used to be. You'll see on a Sunday as well, they've introduced two hours of standard time. It used to be all off peak. So these are issues that we have to take into account, and it gets highly complicated. Hence the use of these optimization packages. So we pump all of that data into the system. If we looked at the load profile, and remember we're looking at a dairy farm, we notice that there's 2 periods when they do the milking, of course. And this is data actually from New Zealand. So you can see what a typical load profile looks like. So we typically look at one day, in other words, from midnight to midnight, 12 o'clock midday through to midnight, and we look at load profiles. And a lot of technology used in a modern milking parlor, all of them needing good quality electrical power, uninterruptible power. You can't get the cows to hang on while you for a couple of hours if you have load shedding. So these are issues that have to be addressed. Now, we're going to show you a couple of load profiles, and this is typically what they look like. This is a load profile, a synthetic load profile that I generated based on data that we have at hand. I'll be talking to Steve as well about some of his clients. We're going to get probably a better load profile. But this load profile does something that might be fairly unusual. We've loaded it in the late night because we're doing 2 things. First of all, we're going to be running irrigation, okay, and we'll be running electric vehicle charging. So you can see the load profile drops typically in the morning in those 2-3 hours when energy is very expensive, and we drop again in the early evening when again energy is expensive. Otherwise, the profile is kind of like what you see. We've compared it to profiles in Europe as well. So this profile you see here is day 1 and day 2, a typical 24-hour cycle, day 1 and another over here. We're looking at between 10 and 100% of 100% represents maximum demand. That's how we start to look at the energy consumption. So it's either kilowatts or scaled according to maximum demand. So if we take this typical load profile, we start thinking about what we're going to be doing with a lot of electrical energy especially for electric vehicles, because it's important to understand the load. And the truth of the matter is, whilst we're probably not going to see large electric tractors there are literally hundreds of small farm electric vehicles. We'll see certainly small tractors. A lot of it is to do with the logistics, moving staff and materials around the farm. These three-wheel Chinese vehicles are manufactured by the millions in China, used all over China, and they're electric. You can charge them. Clearly in South Africa, we probably prefer the UTVs or the ATVs, the little four-wheelers. But there's no doubt that a lot of electric vehicles are available. But if the truth be known, South Africans are not really going to get excited with this until we start talking about the double cab bucky. Okay, so if we had electric double cab buckies, then suddenly every farmer, every South African would be very keen to look at electric vehicles. Let's take the Ford F-150. It's a massive vehicle. Okay, 550 kilometer range, 0 to 100 in 4 seconds. That's faster than a Golf GTI. A massive battery. You can plug in your power tools. You know, as for a farmer, this is great. So you can go out onto site anywhere, plug in jackhammers, saws, everything, all electric equipment, and a very useful vehicle to have. On top of it, one of the other American Rivian vehicles has a slide-out kitchen with electric fridge, electric cookers. Clearly a good idea. But if the truth be known, most of our electric vehicles are going to come from China. So that yellow vehicle at the top left is Korean. And the rest of them are the BYD Shark, for example, is widely available throughout the world at the moment. We're a bit slow in South Africa, but so I really do think that double cabs are going to be the turning point. South Africans love their buckies, and if we can show the farmers that double cabs can be fueled with clean green electrons at a very low cost, we'll see a lot of EVs. So going back to it, we're going to see a lot of demand at night. Now, the problem there is, of course, as everybody will tell you, the sun doesn't shine at night. So how do we handle things? We genuinely have to start understanding that although PV is very attractive and PV is low cost, we need energy at night. So we'll have a look at that in some detail. But before we go there, it's very clear. And to you on Monday, the Business Day published this document about the weather-related claims. It's a big issue in South Africa. Solar is probably at risk of the change in climate, and we've got to start thinking about that and taking that pretty seriously. And there's no harm in having an alternate source of generation on site. Batteries are wonderful, but you do need to charge them. And the grid is, as we've pointed out, the grid is getting pretty expensive. On farms, weird things happen. Young farmers have guns. If they're not shooting at road signs, they start shooting on the bottom right here at PV panels. PV panels burn the connectors. The point I'm trying to make is that, and I'm not picking on solar alone, but the cost of photovoltaics needs to be thought of carefully, because there's a need to understand it and to account for it. So if we jump straight in here, we start having a look at a set of recommendations that come out of this optimization system. So for that particular load profile we showed you, if I just go back to it briefly here, we're probably looking at about 60, 70 kilowatts, probably 100 kilowatts peak, right? So it's a fairly large system. So we've got to figure out then how to allocate the money. Now, the system recommended a 44 kilowatt DC solar system, around about 800,000. Everybody's got a mate who can get you a better price than that. The wind system came out at roughly nearly 3 million. This is the CAPEX cost. And of course, the batteries are sitting at about 500,000. So if I take my engineer's hat off and put the financial director's hat on, all I want to talk about is CAPEX and OPEX. So there's your CAPEX costs for this particular system. Let's have a look at the performance and see where we're going. At the moment, using the 2025-2026 Eskom Ruraflex tariff, we see that these are the savings we can achieve. So our upfront capital cost is 4.5 million. And to get your hands on that sort of money, you need a pretty good business case. And that's, you know, as I said, we need something that's bankable. You need detailed calcs to show that. The first year O&M costs, the OPEX costs were around about 43,000. Okay. Now, it's taking, without any renewables, without the system at all, the farmer would be paying about 360,000 Rand a year to Eskom for that load profile we've showed you. With the system in place, he's only paying 155, gives you roughly a saving there of 204,000, okay? Your net present value over 20 years, because the banks like to see a 20-year set of calcs, comes out looking pretty good. The important ones are probably the payback. So this is a simple payback of roughly 8.5 years. Now, if you talk to the solar guys, of course, they'll say, well, we get payback 3-4 years. And they're probably right, but remember, they're only looking at year 1 or 2, whereas we're looking at the full 20 years. We're escalating all the different costs, and we're making sure that we have sufficient funds to cover the OPEX costs, because systems don't last forever. You've heard Steve allude to the lower cost of wind, which is great. We factored all of this in, and internal rate of return is around about 12%. Now, I'm hoping to do further models. I reckon that we could get it up to 15, which is really something that the banks like to see. And then lastly, you can see the cost of energy. So if you go back to the Eskom tariffs, remember I said at peak times you're paying around about 7 Rand a kilowatt hour. And here's the costs for PV and for wind. Wind is marginally cheaper because of the scale that we've set that out. Bearing in mind, of course, that this model looks at a higher wind area. I think the average wind speed is probably 8 to 9 meters a second. So, you know, when we start looking at this sort of detail, I think it's important to better understand how and why wind plays a part. So if we look at the weather data, typically, you know, this is sort of September time period, you'll see that often enough at night the wind blows and in the day the sun shines. And this is a couple of days in a row where there was beautiful sun. The other interesting thing is, let's just jump to that one there, is the wind definitely does support the solar. In this case, we had a windy period, and you can see that the wind is far exceeds the solar. On some days when the sun doesn't shine, you've got a lot of wind. And you can scroll through the entire year and you can see things like this. Clearly, we do need to better understand how the wind blows and when it blows. So wind forecasting is pretty important. Look ahead systems are pretty important. We've got a fairly good idea of what the solar is going to do in cloud cover. We can actually get cloud cover predictions from satellites to the nearest 30 minutes these days. But when it comes to understanding wind, South Africa needs a lot more data. Satellites don't always pick up wind speed that well. But having said all of that, there's a number of, well, dare I say it, a number of artificial intelligence systems now that can, to a degree, start predicting what's going to happen with your wind. And any look-ahead system will know when to charge the batteries and how to deploy the battery energy. So with that, I'm going to wind this down and just say to you that probably after Easter, we probably run another fourth webinar on wind and take a good look at comparing the Night Save rural tariff from Eskom with the Ruraflex tariff, and also look at dairy farms, greenhouses, blueberry farms, and the table grape industry down in the Cape, and start looking at their load profiles and try and better understand where we're going to be going with our mix of energy, solar versus wind versus batteries. So that's, at this point, I'm going to just leave it there And I'm going to invite my colleague Henry Karosky now to step in and start presenting, rather taking questions. I gather he's got a couple of questions to ask himself. He's going to hold Steve and my feet to the fire and demand a couple of answers on a few things, I guess. So Henry, can we hand it over to you? If everybody could just fire up their cameras, please.
Okay, good evening all. Please, if you have any questions, let them roll in. In the meantime, I have a very relevant question here from somebody. What about with respect to the turbines? What about NRS 097 certification? In the case of where you're going through the DAIA or Sunsec inverters, obviously that will be covered. In the case where you are going AC coupled, Steve, what would be involved there? Is there certification on your products, and what is the general status?
Okay, so when we're doing AC coupling to the gen port or the backup port of the DAIA, Sunsec, Solus, Victron solution, because we're coupling to the inverter that is coupled to the grid, that is a bypass on the NRS. In other words, we don't have to conform to the NRS with that configuration. Because the actual device connecting to the grid is not the grid-tied inverter, it's the grid-tied wind turbine inverter. It's the physical hybrid inverter that you're utilizing to couple to the grid. So from the NRS certification aspect, there is no problem there. The problem that we do have is if we have to connect to the grid side of the hybrid inverter, then the grid-tied wind turbine inverter has to be NRS certified, but we have a workaround for that. Then we utilize a Solus grid-tied inverter, because all of the Solus inverters are NRS approved or NRS certified, and we DC couple to the MPPTs on the Solus grid-tied inverters. So that is a method to get around that. But we are busy working with Solus to improve the MPPT sort of protocols and stuff to support wind turbines better. And it works well in high wind areas, but if you're in an area where you've got 5, 6, 7 meters per second averages, then it's not going to be that effective. But hopefully that answers your question.
No, thank you, Steve. It raises also the question where you have, sorry, I'm losing track of where I was. I'll come back to that question. One that comes up is positioning of the wind turbines. Particularly in domestic environments, people look at that and they say, well, can I use it here? Is it viable in a domestic situation versus a farm or a slightly larger business environment? What is the viability of these turbines in a domestic environment?
Okay, so in the domestic environment is very much determined by the neighbors, because municipalities will not allow, a wind turbine to be installed unless all of the neighbors around where this turbine is going to be installed gives permission. Now, I've recently had a client where he's in an excellent sort of wind area. It's a sort of like a closed retirement community, and he got permission from the municipality. It's near Craddock. Average wind speed is about 8 to 9 meters per second. It would have been a perfect solution for him, but because his body corporate didn't like the idea or the aesthetics of the wind turbine, he was not allowed to install it there. So we had to install a solar solution for him there. So you do get problems like that. But then we have clients. I mean, we've got a client that lives in Hout Bay. He's had a wind turbine up for, I don't know, 15 years, and he hasn't had any problems. But Hout Bay is sort of like a republic of their own. It seems like they can do what they want. But there are certain areas where there's specifically height limitations, like Pinelands in Cape Town. For some reason, you're not allowed to put a tower up higher than 7.9 meters. But if you go to industrial area, what's that big industrial area in Cape Town? We've got a project that's coming up there soon where we're installing a 10 kilowatt turbine on a 15-meter pole on the 3rd floor of a mothballed factory. So, and the legislation says, the moment your tower is higher than 50 meters, you've got to get an environmental assessment study done. But the legislation doesn't say the tower, if the tower is on top of a building structure, it can still be 15 meters high. But because it's in an industrial area, they managed to get it passed through. So each individual sort of wind turbine solution would require a little bit of footwork, a little bit of effort speaking to people. I know the city of Cape Town already has an SECG in place for wind power, specifically for wind turbines. And I think the other municipalities are going to follow suit there. So again, I hope that answers some questions.
Yes, indeed. Thank you. Sorry, I'm staying on you for the moment, Steve. Just a thought I had about this this is a fairly esoteric question. Have you considered with the blades, we talk about these long blades, you were talking of 2-meter plus blades. Have you considered, or who has looked into blade aspect ratio? Perhaps to go to low aspect ratio blades, there'd be a great convenience in reducing the diameter, but how would it affect the efficiency?
That's a very good question. So I've had lots of people approach us with a lot of interesting ideas when it comes to wind turbines. One of them was the Archimedes screw, which they believed would be the next thing, the best thing since sliced cheese. But you do have aerodynamic issues and stuff, and like I said, I'm not an engineer, but I believe we already have a solution where a lot of these guys install more smaller blades to reduce the blade diameter of the turbines. Now, the problem is the more blades you add, the more noise you add, which sort of detracts things from the sort of the attractiveness for a residential application, if that makes sense. From the studies that I've seen, the most efficient wind turbine blade is a single blade with a counterweight on the other end, because it's got the least amount of negative turbulence generated by the blade in front of it, if that makes sense. So yeah, I mean, I'm sure you can increase the blade surface to a certain extent, but there would be a limit to how much you can increase it to reduce the length of the blade in ratio. I haven't personally done any investigation into that, but I believe it is a worthwhile sort of idea to investigate.
No, thank you, Steve. Obviously, that's an area that's going to require a lot of research. Mike, you presented us with a study on specifically on a small farm. Have you looked at other areas in small businesses, maybe in a small industrial park? Could you probably, this is a bit of an unfair question, but can you comment on how it would apply to, say, a small business park?
Yeah, Henry, definitely. So next month we've got the Eskom guys are going to be presenting on their work on an industrial park, and they're including wind into it. My own experience is that the industrial park has a load profile usually where they work 4.5 days a week. Okay, for union rules and other reasons, Friday afternoon is taken off. So for 2.5 days a week, that factory is often empty. with no production taking place. And there's a very interesting set of financial dynamics that come into play when you have a load profile, a 4.5 day load profile. The dairy farm, of course, is easy because the cows need milking 24/7, 365. But the factories work 4.5 days. And of course, we're now starting to see that a lot of factories have electric vehicles, and they're going to be wanting to charge those electric vehicles, delivery vehicles, staff bus, all those sort of vehicles overnight. A lot of factories that work 4.5 days actually work 2 shifts. So they would typically work till 10 at night. And if they're on the Megaflex tariffs, the Eskom or even the municipal time of use tariffs, there's a strong need for energy at night, for early in the evening. As you know, the peak, the peak at the moment is pushed into well, the latest one is now pushed the 3-hour period into the evening from 5 o'clock till 8 o'clock, and that has a direct effect on factories that run 2 shifts. So they're going to need batteries, but batteries are expensive, and the ability to generate energy at night becomes pretty important. And I think that's the driving force the driving force behind looking at wind turbines.
Thank you, Mike. That's certainly something to think about. I have one final question, well, comment from both of you. I think a lot of people out there are looking at domestic usage, and obviously solar at present reigns there. How would you look at the costs and the effectiveness of wind for domestic use? Steve has already highlighted that mounting can be a problem. I'd appreciate a general comment from each of you on that, in that regard.
All right, Steve, over to you first, and then I'll jump in. Thank you.
Okay. Yeah, there's one thing I wanted to mention to Mike as well. As with that little calculation that you did there, what was the energy tariff that you used on the wind turbine calculation, or for that dairy farm?
Oh, the tariff, the Eskom tariff you're talking about?
The Eskom tariff, yeah. What was the Eskom tariff you used for your?
Well, we used the 25/26 Ruriflex tariff, which is a time of use tariff.
Time of use, okay. Right,
yeah, so it
right.
varies according from all the way from, I'm just looking it up here, from about R1.16, including VAT. Sorry, yeah, R1.16, including VAT, up to R7 roughly.
All right, makes a lot of sense. Okay, so interesting question there with regards to the residential. So we are currently busy with a project for a client. He's building his own little, call it a little homestead. It's in a very well-known little town in the Eastern Cape, Bathurst. There he's installing a 2 kilowatt wind turbine with a hybrid inverter system, lithium batteries, solar panels, completely off-grid independent. Now, there's lots of towns and places around South Africa where residential wind turbines are feasible, but we also need some political will. In other words, people on the ground that can sort of encourage municipalities to accept wind turbine solutions and be a little bit less restrictive when it comes to the mounting structures and the towers and stuff. So we have a solution for residential applications. In Jeffreys Bay, we have a solution there, and that's in quite a strict municipal area, where we installed a standalone tower instead of a guide wire tower. And the neighbors and the municipality accepted that solution. You know, it just, like I said before, each solution is almost sort of like a bespoke solution that you've got to take on help the client to either get the approvals that he needs to get. Our tire manufacturer has a lot of contact as well in the municipality, so he helps us a lot as well. And then, like I said, I mean, City of Cape Town, residential now, wind turbines. I've got a client that's in Milnerton, and she has a 2 kilowatt wind turbine installed in her property, and she got all the approvals from the municipality without a problem. So there is a trend where this is becoming more and more acceptable. But I think the higher the demand for this becomes, the more you're going to find that the municipalities are going to start falling in line and actually accept it just as much as they do with solar power.
Great, thanks, Steve. And I'll chip in on the residential. So last month we had Dr. Gareth Erford, and he did discuss residential installations. I think he was looking at a 600 watt unit. So if you go back to our TV channel, the webinar is there, you can watch it. There's a QR code on the screen at the moment, bottom left-hand side. For those of you with an interest, Minx has just let me know that if you go and have a look at the chat box on the screen, there is a link to the registration for our third webinar, which is running, I think, the 2nd of April. And that's where we'll have the Eskom guys and, of course, the CSIR guys to talk about wind potential. Because as you've heard from Steve, we've got to have wind. You've got to know where the wind is. And the wind is not quite like the sun. The sun is to a degree predictable. Kind of shines everywhere, but the wind is a more difficult animal. So the CSIR guys are going to give us some data about the wind atlases and how you can better understand the wind potential at your particular site. Minx also points out that along with Steve's PDF documents, you can download the latest March issue of the What Now? That's the South African Institute of Electrical Engineers What Now magazine, which was published today, so you can download that. And thanks, Henry. We're running into the half hour now, so I'm going to wind it up. I'd like to thank Minx, of course, for setting all this up and driving the system. I'd like to thank Henry for acting as our question master, as our host, and especially to Steve. Steve, that was a really great presentation. I'll repeat what I said at the start. I think there's going to be a lot of people that really wish that they've known you for longer some years ago, because this understanding of small wind is critical. Personally, I don't believe we should be going off grid. I think we need to remain connected to the grid so that we can buy and sell energy via the grid at some stage. And of course, going completely off grid, you take a lot of responsibility and of course a lot of costs. So all the bigger solutions I think that people are going to be looking at are going to be grid tied, grid connected, and integration with the grid is important. And I think we're going to see a lot more about grid forming inverters in the near future. So Steve, thanks. The last word to you, and then we'll wrap up.
Thank you very much, Mike. I really appreciate this opportunity. Everyone have a wonderful evening, and God bless. Thanks.
Thanks, guys. Thank you. So we'll wind up now. Thanks, Minx. Yeah. Good night, everybody.
Thank you to Mike. Thank you to Steve, Minx, and everybody for attending. Good night.